Hello, so today I will try to explain what will be the goal of these lectures. Right? As you probably expect, if you have in R an interval AB, let's say open at A and closed at B, you know that the length of this interval AB, which I will represent by lambda of AB, it's given by B minus A. Right? So what we would like to do in these lectures is to extend this function to a function which is defined on all subsets of R. So my goal will be to try to find a function, lambda, which is defined on all subsets of R, and I'm representing by P of R all the subsets of R, to the sets R plus union plus infinity, which extends the idea of length. So it's clear what we mean by the length of an interval. We would like to extend this idea to a function which is defined for all subsets of R. So what would be the natural extension of, say, let me call this function measure. The measure of an interval is B minus A. What would be the measure, say, of the rational numbers or the rational numbers between 0 and 1? So this is the type of question we would like to answer. And what are the properties we expect lambda to satisfy? Well, first, I think you all agree that, note that I'm defining lambda as taking values in R plus, union plus infinity. Eventually, if you take an infinite interval, its measure will be plus infinity, so I have to add plus infinity. But what else would we like to have? Well, first, let's say we would like to define it for all subsets of R. Then, let me rewrite this, so let me call this property, say, property 0. We would like the measure of an interval AB, which can be open or closed on the left, open or closed on the right, as B minus A. What else we would like? Well, I think you all agree, let me represent by 2 a second property, which means that if you take a set and you just translate it by a certain number, it's natural to ask that the measure of this set is equal to the measure of the set translated by X. So let me represent, if A it's a subset of R, let me represent by A plus X the set of all points X plus U, where X plus Y, where Y belongs to A. So what I just said is that for all A subsets of R and for all X in R, we would like this function lambda to be such that, well, the measure of the set A plus X, so the translation by X of the set A, to be equal to the measure of the set A. So this is a natural condition. And then there is a last condition, which is also quite natural, which is that, well, if a set is a union of disjoint subsets, so let's say that A it's equal to the union of AJ, and if these sets are disjoint, which means 2 by 2, which means that AJ intersection with AK it's empty, well, it's natural to ask that the measure of A to be equal to the sum of the measures of the set AJ. So I will require this function lambda to be such that the measure of lambda to be equal to the sum of the measures of AK. So my goal will be to try to define a function lambda with these 4 properties. It has to be defined for all subsets of R. It has to be an extension of the idea of length, so the measure of an interval should be equal to the length of this interval. It should be invariant by translations, so the measure of a translation of a set should be equal to the measure of the set. And finally, it should be what I will call later sigma additive, which means that if a set A can be written as the union of subsets Aj, which are disjoint 2 by 2, then the measure of A should be equal to the sum of the measures Ak. So this would be a goal, try to define such a lambda. So today, what I will do is that I will show that this is impossible. So I will start by assuming that there is such a function, and I will reach to a contradiction. And to do that, we will use the axiom of choice. Right, so I just wrote here the 4 properties I'm assuming that lambda satisfies. So property 0 is that it's defined for all subsets of R, that it's an extension of the length of an interval, its translation, it's invariant by translation, and it's sigma additive. Assuming all these 4 properties and the axiom of choice, I will reach a contradiction. So this is what we will do now. To prove that, let me introduce in R an equivalence relation. So I will say that x and y are equivalent for x and y points in R if the difference between x and y is irrational. So this defines an equivalence relation in R, and I will represent by this symbol the class of equivalence of x. So this is a set of all points in R which are equivalent to x. So these are all y in R such that y minus x is irrational. And let me represent by lambda this set of equivalence classes. So these are, this is the set R modulo this equivalence relation, and I will represent the points of lambda by the symbols alpha, the Greek letters alpha, beta, and maybe gamma if I need gamma. So it's clear that gamma is not countable. Because if lambda is countable, then since these sets are countable, R would be countable, because any point in R can be represented by an element of lambda and an element of the equivalence class. So lambda, it's clearly not countable. Its family, the set of all equivalent classes which we defined above. So what I will do now is I will construct a new set which is obtained as follows. So lambda, it's a set of equivalence class. It's an uncountable set, and each element of lambda, it's in fact an equivalent class. So a set, a family of points. Well, what I will do, I will use the axiom of choice in order to, for each equivalent class, I will take an element of this equivalent class, and in this way, I will form a set, omega. So omega is a subset of R which contains one and only one point of the equivalent class of lambda. So let me explain it again. Lambda, it's a set of equivalent classes. So each point alpha of lambda represents an equivalent class. It's a set. So for each point alpha of lambda, alpha it's an equivalent class, so it's a set, a countable set. I will choose one point, and I will form in this way a set omega. It is clear that I can always choose a representative of this equivalent class which belongs to the interval 0, 1. So in fact, I can assume that omega it's in fact contained in 0, 1. Right? Because if I choose an element of this equivalent class which belongs to 0, 1 in the construction of the set omega, I obtain that omega it's contained between 0, it's contained in the interval 0, 1. Right? So maybe this is the main step in this proof that it's not possible to construct a function lambda with the 4 properties. It's the construction of this set omega. Now I will prove some properties of omega. What I claim is the following. Take the set omega plus q and the set omega plus p, where q and p are rationals. What I claim is that either these two sets are equal or they are disjoint. So the intersection of omega plus q with omega plus p is the empty set. So what we'll prove is this dichotomy. Either these two sets have no intersection or they are equal if q and p are rational numbers. So let's prove this claim. To prove this claim, I will assume that this intersection is not empty, and I will prove that in this case these two sets are equal. So let's assume that omega plus p intersection omega plus q is not empty. And let's take, therefore, a point x in this set. Since x belongs to omega plus p, x is equal to some alpha plus p, where alpha belongs to omega. Well, on the other hand, if x belongs to omega plus q, x is equal to beta plus q, where beta belongs to omega. Therefore, I have that alpha minus beta, it's equal to q minus p. Well, q and p are rational, so q minus p is rational, which means that alpha minus beta is a rational numbers, which means that alpha and beta are equivalent, but since in the construction of the set omega I took just one element of each equivalent class, this means that, and since alpha and beta are equivalent, this means that alpha is equal to beta. Well, but if alpha is equal to beta, q is equal to p, and therefore omega plus p is equal to omega plus q, proving our first claim. So we just proved that if we take two rational numbers q and p, which are different, then the set omega plus q has no intersection with the set omega plus p. So let me consider the set sum over all q, which is a rational number, q between -1 and 1 of omega plus q. Right, so I'm taking, let me just first set a notation. Whenever I have disjoint subsets, instead of writing the union, I will write this symbol to mean that I'm taking the union of disjoint sets. So here I'm taking the union of all sets omega plus q, where q is a rational number between -1 and 1. And what's important to realize here is that, well, these sets are all disjoint by the claim I proved a minute ago. Now let's see. I have a second claim, which is clear, is that these sets omega plus q are all contained between -1 and 2. Because omega, by our construction, it's contained between 0 and 1, and q, it's contained between -1 and 1. Therefore, if I translate omega by q, in the worst case, I'm bigger than -1, and in the worst case, I'm also smaller than 2. So it's clear that all the sets omega plus q are contained in the interval -1, 2. In particular, if I take the union of all these sets, since each set is contained in the interval -1, 2, the union is also contained in -1, 2. So this set here, on the one hand, it's contained in -1, 2, which means that the measure of this set should be less or equal than, so let me prove that, then the measure of the interval -1, 2. So let me show you why this inequality holds. Well, what I claim is that what I'm using here is that if the set E is contained in a set F, then I have that lambda E, it's less or equal than lambda of F. Right? Why this is true? Well, because I can always write F as E union F minus E. These two sets are disjoint. Lambda F is equal to lambda E union F minus E. By our property 3, if I take A1 to be E, A2 to be F minus E, and all the other sets to be the empty sets, this will be equal to lambda E plus lambda F minus E plus the measure of the empty set, but the measure of the empty set, it's equal to 0, because I can write always the interval, say, -1, 1 as -1, 1 union the empty set, union the empty set, and so on. To use this relation to say that the measure of this set, which is 2, it's equal to the measure of this set, which is 2, plus the measures, infinite times the measures of the empty set, which has to be equal to 0 to satisfy this identity. So it's clear that the measure of the empty set is 0, and therefore, by using property 3, I can conclude that the measure of the set F should be equal to the measure of the set E plus the measure of the set F minus E. Well, if the measure of this set is plus infinity, I get that the measure of lambda f is plus infinity because lambda takes only non-negative values. So if lambda f is the measure of the set f minus e, it's plus infinity, lambda f is plus infinity, in which case this inequality holds trivially. On the other hand, if this set has finite measure, well, we do get that the measure of lambda f is greater or equal than the measure of E. So in both cases, we can conclude that the measure of the set E is less than or equal to the measure of the set F if F contains E. So I can apply this identity this inequality which I just proved here. We've seen that the union of these sets is contained in the interval minus 1, 2, and therefore the measure of this union is smaller or equal than the measure of this interval, which is equal to 3. So I have a bound on the measure of this set. On the other hand, by property 3 again, which tells us that the measure of a disjoint union is equal to the sum of the measures, applying this property 3 to these sets, which are disjoint 2 by 2 as we have seen, the measure of this union is equal to the sum of the measures. And we've seen that this sum, well, the measure of this set, it's less or equal than 3, which is what I'm writing here. Then, now, property 2 tells us that if I take a set A and I translate it by x, its measure is equal to the measure of A. Which means here that all these sets have the same measure. Since this sum is bounded by a finite number, it must be equal to 0. So we just conclude that, well, if all the properties of lambda we wrote hold, we have that lambda of q plus omega, which is lambda of omega, should be equal to 0, right? Because if it were to strictly positive, this inequality could not hold. So we concluded that the measure of omega, which is the measure of q plus omega, has to be equal to 0. So up to this point, we proved that the measure of these sets omega plus q are all equal to 0, and therefore that the measure of the union of these sets for q rational between minus 1 and 1 is equal to 0. Now I claim that the set 0, 1 is contained in this union. Okay, so to prove this claim, let me fix a point x in 0, 1. let me take, so I know that there exists a point alpha in the equivalent class of X, which belongs also to the set omega. And remember that this point, so remember that in the construction of the set omega, we chose one representative of each equivalent class. So one of the points, it's a representative of this class, and we chose this point in 0, 1. So alpha also belongs to 0, 1. Well, so since alpha belongs to the equivalent class of X, we know that alpha minus X is a rational. Alpha minus X, I'm sorry. Alpha minus X, which I will call Q, it's a rational. Because alpha and X are equivalent. But alpha, it's a point in 0, 1. And X, it's also a point in 0, 1. So this means that alpha minus X, in the worst case, alpha is 1 and X is 0. So Q is smaller than 1. And in the worst case, alpha is 0 and X is 1. So Q is also bigger than 1. So this rational Q has to be strictly greater than minus 1 and strictly smaller than 1 because alpha belongs to 0, 1 and X belongs to 0, 1. Which means that X it's equal to alpha plus Q, where Q is a rational number between minus 1 and 1, which means that X belongs to omega, because alpha it's a point in omega, plus Q for some Q rational between minus 1 and 1, and this is exactly what it's claimed here. Again, since this set contains that one, we know that the measure of this set has to be greater or equal than the measure of this set. The measure of this set is 1. So 1, it's smaller than the measure of the union over all Q between minus 1 and 1 rationals of omega plus Q. Right? Which is in contradiction with what we proved before, because we proved before that the measure of this set is equal to 0. So here is the contradiction showing that it's not possible to have a function satisfying all these 4 properties. So this was my statement at the beginning of this lecture, that it's not possible to construct a function, lambda, which is defined on all subsets of R and which takes non-negative values and or plus infinity, and which is an extension of the length, so which which maps the interval AB to the length of the interval AB, which is invariant by translation and which is sigma additive. So this is unfortunately not possible. So what can we do? Well, we would like very much to extend this function, a function which extends the notion of the length of an interval. Well, since we are not able to define a function with all these 4 properties, we will have to accept to remove one of these conditions. It's clear that we don't want to remove condition 1. Well, it's also clear that we wouldn't like to have a function which is not translation invariant. Also, our intuition tells us that if you take sets AJ which do not have intersection, it's natural to ask that the measure of the union to be the sum of the measures. So the point here is that we will accept to have functions which are not defined at all subsets, which means that there are some subsets of R to which we cannot associate a measure. These will be called the non-measurable sets. And the goal of the next lectures will be to start with a function which is on the intervals defined by property 1, and step by step extend it to the largest possible family of subsets of R. So this is what we'll do. In view of what I just proved today, which is that it's not possible to define a function with all these 4 properties, well, let's try to see how far we can go. So for which is the largest class of subsets of R for which we can associate a measure. And this will be the goal of the next lectures.